Right. So, I guess we're gonna have. But before I start, let's talk a little bit about like how the homework is gonna work. Somebody asked me this earlier. So next week on Thursday during the lab day, I'm just going to verify that people have been working on their homework. So that means that I'm going to look at either paper that you guys have accumulated that shows the work that you've done. But a lot of people in here are working on tablets. You can just scroll through and show me. That is just for completion. Did you do the work, right? And if you have extra problems, that's great. But I'm just going to verify and see that you've been like working along with the class. The actual verification that you are getting the answers right is going to be when I give you this quiz that I'm giving you today and next week. It covers the stuff from the homework. And then that will be graded separately. So the homework essentially is just an effortful thing. You do the homework, I'll give you credit for it. The quiz is going to be actually graded. I'll give you real feedback on how you're doing. And the first one I don't think is that complicated. It'll get more, they'll get a little bit harder as the class goes on, but I'm always going to give them at the end so that people can leave early if they're finished. You can work to the end if you're not. And it's just convenient to do it. And this normally I give them at the beginning, but for this class, because of the timing, it's convenient to do it at the end. And then, yeah, so what we're going to start with today is going to be section 1.2. So this is, we're really leaping into complex analysis for real now. And so, actually, so I make sure I don't write off of where I can see my camera. Myself some weeds marks here. I mean, these classrooms really, like, you know, a lot of classrooms have built-in recording capacities at a lot of universities. I don't think they do it here. So. A lot of projectors, though. All right, so let's actually. So last time we pointed out, sort of in the course of the lab day, I pointed out the reason that we think of, you know, like e to the x and the power series for e to the x. And so we did this thing last time where we started with the power series e to the x. We said that was equal to 1 plus x over 1 factorial. This is really a Maclaurin series because it's centered at 0. And I did something maybe unjustifiable with that. So where does this converge? We didn't answer that last time when I was talking about this. Where does this series converge? So it converges for every real number, right? This is infinite radius of convergence. You learn this when you study calculus, that this has r is equal to infinity, or radius of convergence is equal to infinity. Does anybody remember where that comes from? So typically, the ratio test is a place where it generates it, right? So when you're computing a radius of convergence of a power series, you do a ratio test to the coefficients. So you get this with the ratio test. And what the ratio test says is that if you have a series that looks like actually, what does the ratio test actually say? Let's start with that. Just the ratio test from real calculus. The ratio test says if you have some series, not power series, just some series, how can I test for convergence of it? I don't think people take that here. Take the n plus 1 coefficient divided by the n coefficient. You take the absolute value, take the limit as n goes to infinity, and what needs to happen for that to be equal, for this to converge? This has to be less than 1. If this limit is less than 1, you have convergence. If this limit is greater than 1, you have divergence. And if the limit is equal to 1, you have sadness is a good, yeah. Despair. You could say nothing, right? If you're at the equals 1 case, you have no information about what's happening, right? So there's this borderline case. This is actually connects up with why we think about open domains when we're talking about complex numbers, right? Is I don't care about the edge because a lot of times I'm going to be working with power series and I don't know what happens at the edge. So I just ignore it. Who cares about the edge? So, no, I'm sorry, the answer was sadness. Okay, so we'll go with sadness. Okay. So, how did that work with power series? So this is a test for numerical series. How does it work for power series? Like, what do we actually do? So remember that a power series, a real power series, was of the form f of x is equal to the sum from n equals 0 0 to infinity of a n x minus, let's call this Cn. X minus a to the n, right? This is called a Taylor, that's not a Taylor series, power series. This is a power series. So how did you use the ratio test when you're working with power series? Yep.
You try to force the term that's being raised to the nth power to be less than 1, and after value is less than 1.
Yeah, so like what ends up happening is you end up sort of sequestering anything. You basically try to get it down to the point where you had these x minus a's, and everything else lived inside these coefficients, right? Everything. Every numerical bit of information was in here. And what you ended up with at the very end, if you do the ratio test on something that looks like this, what you end up with is something that looks like the limit as n goes to infinity of the absolute value of Cn plus 1 x minus a to the n plus 1 divided by Cn x minus a to the n. And if you grind that computation, what you end up with is the limit as n goes to infinity of Cn plus 1 over Cn times the absolute value of x minus a. Normally what happened here is you ended up, this is breaking stuff, you ended up with this term over here that maybe it wasn't a pure x minus a, maybe there was another number in here, like a 2 or a 6 or something. And the idea was this limit was just whatever it was. This limit of Cn plus 1 over Cn, that's going to go somewhere if it goes somewhere, just like over here. But what we end up doing is we pick the x values that make this quantity less than 1. So it's like we're using the ratio test to explore where the power series converges. We're finding the x values that make the ratio test hold. And once we have those x values, we call that the interval of convergence for the power series. The answer that came out of this is twofold, right? There's a radius that measures, like this tells you how big the disk can be. What you should think when you look at something like this, what I want you to think of about an expression like this is, this tells you that you're looking at some sort of disk. It's a disk because it's got a center of A, and you're looking at distances from points x to some center A. So this is a disk of some radius. What radius does it have? Well, this tells you something about the radius of the disk. Well, essentially what you're saying, if you want this to be less than 1, is that after you account for this number, you really want these things to be smaller than whatever that radius happens to be, right? So normally what you do is you call this quantity over here something cheap. This is the math book move, right? You call this 1 over r. You say 1 over r is this limit right here. And the reason you call it 1 over r is because if you multiply both sides by that, you end up with the statement x minus a is less than r. And so this quantity, this limit right here, is the reciprocal of the radius of convergence. The ratio test expressly tells you the radius on which this thing is going to converge. The distance you can get away from A and have this power series converge. Sorry, I know this board is like, I'm way over here instead of way over there. So what I wrote there was that if you have the limit of Cn plus 1 over Cn times x minus a is less than 1, and you call this limit right here, notice that's not in the limit, so you call this thing 1 over r, then you can multiply both sides by r and you get this. All values for which this statement is true are values for which that limit is less than 1, which means the series converges. Now, normally, when we're doing this, we actually don't use the ratio test, we use the root test. It turns out that the root test and the ratio test have the same answer. If you compute a radius of convergence with a root test and you compute it with a ratio test, you get the same radius. Does anybody actually remember the root test? N through to what?
Absolute value to
Okay. So the root test says if you start with Cn x minus a to the n, n is equal to, say, 0 to infinity, then you can do, that's not a power series, it's n right here, that this thing will converge if this converges, if the limit as n goes to infinity of an to the 1 over n converges. I'm sorry, is smaller than 1.
Is that if or if and only if?
It's an if. It's just like the ratio test. It has the same restrictions on it. Less than 1 means convergent. Equal to 1 means no information. Greater than 1 means divergent. So the root test and the ratio test both give you the same exact setup. If you get to this point, this number, which we can call 1 over r, is the same as this number, which we can also call 1 over r for a power series. Okay? So the root test and the ratio test are ways that expressly tell you. Okay. Yeah.
Just to be clear, A is still like C.
A here, an is just as a numerical series. This is a numerical series, and if you want to apply it to a power series, then you get the same exact type of setup, where now, instead of doing this step with the ratio test, instead you do the limit as n goes to infinity of Cn x minus a to the n to the 1 over n. And again, you can see the same thing happens, right? The 1 over n kills the n, and you end up with the limit as n goes to infinity of Cn to the 1 over n. These are absolute values here, I should say. That's important. Cn to the 1 over n times absolute value of x minus a is less, that will converge when this is less than 1. So again, this is like 1 over r. This number tells you exactly what the radius of convergence of a power series is. This is used numerically all the time to figure out when a power series converges. In either case, the idea is that the root test and the ratio test are extremely powerful tools. In fact, in calculus, you probably don't get the idea of how powerful they actually are. In calculus, when you see Taylor series, you pay basically no attention to this because the ratio test is just a way to force you to cancel factorials against each other, right? But what's really going on here is you are computing everything important about where this power series is a well-defined object, where it's actually a function. So, why does this approach work in complex analysis? Because I'm going to make the claim here that this same exact idea works in complex analysis. Why does it work? It's the absolute value is the thing, right? What does the root test actually say, or the ratio test actually say? It says, if this absolute value is less than 1, then the series converges. The absolute value and complex modulus are basically the same thing. So it turns out to be the case that every single power series that converges with radius of convergence r for real numbers converges with the same radius of convergence if you just stab complex numbers into it. I know, again, I'm sort of maybe giving you the idea that there's no such thing as complex analysis because it's just real calculus, but you just put z's instead of x's. But that's literally what you're doing here. So this has a name. This idea is called the extension theorem. And basically what the extension theorem says is this. I'm going to give you what the secret ingredient is here. A lot of you may not have seen it before. So step 1 in this is something called the Weierstrass M-test. So this is a theorem about the way that series behave that you may or not have seen before, but I think it's important to state it. I'm not going to prove it, but I'm going to state what the M-test says. If you decide to do the 4+1 program in mathematics, you have to learn the Weierstrass M-test to pass the qualifying exam. What the Weierstrass M-test says is that if you have a series that looks like, where the terms look like this, Cn times x minus a to the n in absolute value. If it is always the case that this is less than or equal to some constant mn, so for every value of n, I can find a constant that bounds that term. For all z minus a less than r. So you're in some little disk around a center A, and you can find constants that make this really small.
Is X and Z again?
Oh, I'm mixing x and z together here, sorry. Let's do it with complex numbers. Yeah, there should be z's, right? This is a theorem of real calculus, but it works because it has to do with convergence of series. This is the setup. You start with a power series. It has terms that look like this. And you start with some small disk of inputs. So this is be a little abstract for a second here, but the idea is this shouldn't be a surprise. If you have a power series, but you can replace all the terms with constants, and the constants converge when you add them up, then the power series must have converged when you add them up. It's the squeeze theorem, right? If you had this setup and the sum from n equals 0 to infinity of this numerical sequence converged, then it must have been the case that this converged. For all z minus a less than or equal to r. Yep.
Does it have to be a power series to apply the m-test?
It doesn't. You can apply the m-test basically to any sequence of functions. We're using a particular version of it where we're studying power series, and so we're using this family of functions. But yeah, the m-test is actually quite a bit more powerful than I'm saying here. If you've seen 412, this is one of the key tools for proving that things are uniformly convergent. For us, it's enough to say that if I can take the terms of a power series and bound them above by constants, and the constants converge, then the series must have also converged. Yep?
Is it significant that you're using the closed disk?
It's not. I mean, we can do this too. Not significant. It may just be an artifact of the way I took the notes. Yeah, we're never, in fact, I should probably write it like this, right? I don't care if it converges on a closed disk. So. Right. So now, what does that let you do? So now we have a way of saying, notice these are just numbers, right? These are numbers. And those numbers are positive numbers. Does it matter how I get that sequence of positive numbers? Does this care if these were real numbers or complex numbers? No, because what you're saying is, if you can take this, whatever this is, and replace it with a sequence of positive numbers, then it must converge. Regardless of whether you start with z or x. So this is the tool that lets us shift from real calculus to complex calculus, because the m-test is what lets you prove the root test. So the next ingredient is, now I'm not going to do this in detail, but these are sort of the key tools of complex analysis, are working with these power series. And I will go back and we're going to formally define power series in a second. Okay? I will try to remind you of things you're supposed to remember from calculus here. So these are not complex theorems, these are real theorems. What the root test says is that if, and we're just going to do the root test version of this. If I have a real power series that looks like Cn x minus a to the n is equal to 0 to infinity, and I define the number r to be equal to the limit as n goes to infinity of 1 over the absolute value of a n to the 1 over n. That look familiar? Then the series converges for z minus a less than r. That is the radius of the power series. And here's where we go from real calculus to complex calculus. What we're going to claim is that this still works if I put, this is supposed to be x, that this is still going to work if I put z's right here, because this is an absolute theorem about absolute values. And so let's define what we mean by a complex power series, and I'll state the extension theorem. First off, this is a big lift over what we did last time, because we were talking about complex numbers, and all of a sudden we're talking about power series, right? Power series is sort of the central tool of complex analysis. Are there questions about anything that we've done so far here? I know this is more abstract. Okay. So, a complex I mean, we can say what complex power series is, but I'll just by myself. So a complex power series is just a sum of the form sum from n equals 0 to infinity of Cn z minus a to the n, where all of the Cn's are complex numbers. They could be real, they could be complex, but the idea is it's the same as the power series from calculus, except now I'm going to allow the coefficients to be complex numbers, possibly. Okay? Same exact idea. Now, where do we get complex power series? What's the easiest place to get them? Well, it turns out that because the m-test can be used for complex numbers, and the root test can be used for complex numbers, we get this really striking theorem called the extension theorem. Does anybody remember the power series for 1 over 1 minus x? Or 1 over 1 plus x. No, that's 1, yeah, 1 over 1 minus x. What is that? Yeah, this is right. What is that power series?
1 plus x squared.
1 plus x squared plus x to the third, and so on. Okay, but you haven't told me everything I need to know about it. Where does it converge?
X absolute value less than 1.
Okay. Absolute value of x strictly less than 1. So let's plot it real quick. Where does that function have an asymptote? At 1. Okay, so right here, we've got a problem, right? There's a hole in the function right there. Where is the series centered that we wrote? See, this is centered at 0 because we can think of this as being the sum from n equals 0 to infinity of x minus 0 to the n, right? So the center of that power series is the Maclaurin series is at 0. Now, do you think it's an accident that this thing converges on this band right here in either direction? I mean, the idea is like you start at the center and you go until you hit this asymptote, and then the series can't possibly converge at the asymptote because at the asymptote it's blowing up to infinity, minus infinity. Does that make sense? Like this, the function is not defined here, so how could the power series possibly be defined at that point? The power series has an interval it lives on that starts at -1 and ends at 1. That's what this means. So here's the extension theorem, the fancy extension theorem from calculus. How do I take that and turn it into a complex power series?
It's x with z.
Okay, so if I was going to do that, I would have the absolute. They're all black, dude. That's great. Yeah, I'll just replace that black marker with this black marker. Okay, if I did that, I would get the absolute value of z. What is the absolute value of z less than 1? What sort of shape is that?
Circle.
It's a circle centered at?
0.
Oh. So this is the disk of convergence. Same radius of convergence, right? The r here is the same. This was radius 1. This is all the points of radius 1 away from the origin here. So if I want to know the power series, I want to make this into a complex function, I just do 1 over 1 minus z is equal to the sum of z to the n is equal to 0 to infinity, as long as the absolute value of z is less than 1. If you want to get from real convergent power series to complex convergent power series, literally all you do is replace x with z. Yep?
Does the series converge in the real world when x is -1?
No.
It does oscillate when
I mean, yeah, but the thing is, like, with the thing with, it oscillates, but no, we wouldn't consider that a convergent sequence. I mean, there's basically, anybody who's, like, spent any time working with these things would say, like, if what you have is even conditional convergence, get it out of here, right? Conditional convergence, like, why would you ever work with something where you can rearrange the numbers and get any number you want as the result, right? Yep? Convergence. This is the disk of convergence. So what that means is, if I know a real power series, I also know a complex power series. So, I don't know why I just erased e to the x, because that's what I wanted to talk about. So the extension theorem is as follows. The extension theorem says, let's see if I wrote it in here. Any real value function real value, okay, we're going to talk about some definitions in a second here. Any real valued function f of x is equal to the sum from n equals 0 to infinity cn x minus a to the n with, and this is really important, a positive radius of convergence.
What a negative radius of convergence look
No,
like?
non-zero.
Non-zero,
You're just
okay.
trying to stay away from zero.
Okay.
When you guys learned Taylor series, you learned this stupid case where the power series doesn't exist anywhere except when you plug in the actual value that cancels with the a out, you get a series of zeros. So like here, every power series trivially can be satisfied at the center. We want something where the power series converges on some disk. Remember, everything about complex analysis is convergence on some open set. So any real valued function that has this form, power series with a positive radius of convergence, can be extended to a complex power series with the same arc, with the same radius. So this move where we take the real interval and then just consider it as the diameter of a circle, that holds in general. If I have a function and it has some interval that it has a power series that it converges on, I just draw the circle with that as a diameter and I've got a complex function. And any z that's in that circle is legal to plug into it and will converge. So, yesterday I did something kind of hand-wavy because I walked you guys through an argument that e to the ix was equal to cosine of x plus I times the sine of x. But I did something when I did that. I wrote down the power series for e to the x. I said e to the x is equal to 1 plus x over 1 factorial plus x squared over 2 factorial plus x to the third over 3 factorial. And then I plugged I into it. I replaced x with ix. Was that legal to do? Nobody argued with me yesterday when I did it. But how do I know that ix is in the domain of where this thing converges? Like, what makes that legal? Something has to justify when I took e and I put the ix in there. I just did that without telling you that it was iffy that I did that. And we ended up with something like 1 plus ix minus x squared over 2 factorial minus ix to the third over 3 factorial plus x to the fourth over 4 factorial, so on. You could just compute that's what that turns into, but what justified doing that? Yep. So, if this converges for all real numbers, what's the circle that you draw in the complex numbers? It's all of it. It's literally every single complex number this makes sense for. So it turns out that if you want to know what the complex exponential is, you just put z in place of x and it always works. So the power series for e to the x immediately lifts to a power series for e to the z. So e to the z is the sum from n equals 0 to infinity of z to the n over n factorial. What other complex functions can we cook up here? Yep.
I have a question.
Yep.
If e to the x is supposed to converge with the same radius of convergence, how do you rectify the fact that we're talking about the complex points as opposed to the real numbers?
What do you mean?
Like, we converge for all real numbers.
Yes.
But it doesn't include
So
all
pick-
the complex.
So pick a center,
0.
okay, and then the radius of convergence. So if you do the root test on that, what you're going to get is that the 1 over r value is equal to 0,
Right.
right? So that means no matter what number you put in there, remember it's all in absolute value when you check that, right?
Right.
So you can imagine, put a complex number in instead.
Okay. 3i.
Okay, Now, in absolute value, it's still the case that the coefficients are going to 0 so fast that you got a fixed value of z, but it's in modulus, which is just some number, and the coefficients crush it anyway,
Gotcha.
right? The coefficients are what control convergence. It's a good question. Okay, so that means immediately we get this whole family of functions, right? Like, for example, 1 over 1 minus z is just the sum of z to the n, where the absolute value of z is less than 1. And I don't know, how many power series do you guys know? I mean, am I exhausting the library here? E to the z, 1 over 1 minus z, cosine, sine, and the end. Is that the... Oh, really?
The odd powers.
Oh, yeah, okay. You can do the thing where you like, yeah, arctan is an example of you substitute x squared into the series for 1 over 1 minus x and you integrate it, right, or whatever. Okay. So the idea is that what the extension theorem lets you do is explicitly lift from from real functions to complex functions. This is the central move. And it's why power series are going to be the main tool that we use. So the last thing I'll do before I hand the quiz out here is I'm going to have a couple of definitions. These definitions are important. What does it mean? Okay, we did this last time. What does it mean to say f is holomorphic on some domain D? F is a complex function. I say f is holomorphic. What do I mean?
Differentiable.
Differentiable. So this is equal to differentiable. Complex differentiable. Okay, I want slightly more. At every point in D, I want a little bit more than that. That's a pointwise thing, right? It's a yeah, I need a disk, right? I need differentiable on a disk. Every point in D has a little circle around it, and the function is differentiable on a little circle around every point in D. This, with the way we've written it, is a point-by-point way of checking. When I say holomorphic, I mean not complex differentiable at a point, but complex differentiable at some dRA, a little disk of radius r, for each A in the domain. Not just pointwise derivatives existing, but little circles where the derivatives exist. Yep.
Is that why you need to be working on open?
It is why you need to be working on open sets.
Is that, should it be on some DRA for each?
Complex, yeah,
I'm sorry, I'm just.
it's cool. Yeah, on some dr, it basically just means for each point in the domain, you can find some little circle around that point at which the function is differentiable at every point in that little circle. If you want to think about it in terms of tangent planes, it means that the complex tangent planes vary smoothly around that point. You don't have weird cusps or kinks or anything in the surface that this thing is generating. The function is smooth. All right, F is analytic on D. What does that mean?
Uniformly convergent power series.
That's exactly what it means. F has a uniformly, if you don't know the word uniformly, don't worry about it. We just mean convergent power series in the sense we're used to. F has a uniformly convergent power series. On D. Normally this is defined on some disk, centered at A and to some radius of convergence. These two definitions are the central definitions of complex analysis, and complex analysts are lazy because it turns out that they're equal to each other. But for now, where we are in the class, we have two different sets of ideas we're studying, and we haven't built this together yet, right? The first idea is things have power series. And every analytic function you guys know from real calculus is also complex analytic. So all of these guys, e to the z and 1 over 1 minus z and cosine of z and sine of z, which I didn't write, but you can just imagine they're there. Those are analytic functions because they have uniformly convergent power series. Holomorphic functions mean differentiable. And even weirder, once differentiable is going to imply infinitely differentiable. So if I'm asserting someday that we're going to discover that holomorphic and analytic mean the same thing, what I'm saying is In complex analysis, we're going to have the scenario where one derivative of a function existing is enough to force it to have a uniformly convergent power series, which is not at all the way real calculus works. Okay? So for now, these are two separate ideas. I want you to imagine that we're going to be looking at, when we start one step deeper here, is, I mean, we have examples and things to do as well. So this is sort of a theoretic orientation to where we're going. Holomorphic is about differentiability. Analytic is about power series. And it's magic that those two things are equivalent to each other. All right. So the next chunk of the class is going to be about the extension theorem and things we can do with the extension theorem. We're going to study the complex exponential. We're going to do some examples of working with power series. It'll be more concrete than this, which I know was pretty theoretical. And this is kind of the way this class is going to go. It's going to drift back and forth between theory setups like this and then practical computational examples. All right, so I'm going to shut this down.